Stephen Hawking, explains the great misconception about electricity. Stephen Hawking once said, "The greatest enemy of knowledge is not ignorance, it is the illusion of knowledge." I turn. This profound insight would have guided his analysis of perhaps the most widespread misconception in all of science, what electricity actually is and how it really works. While billions of people use electricity every day and think they understand it, Hawking would have been fascinated by how our intuitive picture of electrical current is not just wrong, it's backwards, upside down, and fundamentally misleading about one of the most important phenomena in the universe. The legendary physicist would have immediately recognized that our common understanding of electricity as Rick's flowing electron search represents one of the most persistent and damaging misconceptions in science education. This oversimplified picture prevents us from grasping the true nature of electromagnetic phenomena and blinds us to the profound quantum mechanical processes that actually govern electrical behavior. Hawking would have been amazed by how this misconception about electricity connects to some of the deepest mysteries in physics, from the nature of electromagnetic fields to quantum mechanics, from the behavior of superconductors to the fundamental forces that hold atoms together. Understanding what electricity really is opens doorways to comprehending phenomena that seem like magic, but are actually manifestations of the universe's most fundamental principles. Think about this mind-bending reality. When you flip a light switch, the electrons in the wire barely move at all. They drift slower than a crawling snail, yet the electrical signal travels at nearly the speed of light. The Monty Treeson's electricity that powers your devices isn't actually moving particles, but rather electromagnetic fields that propagate through space around the wires, not through them. What we call electrical current is really a wave of electromagnetic energy that exists mostly in the empty space surrounding conductors. What if I told you that Stephen Hawking's analysis reveals that electricity isn't electrons flowing through wires like water through pipes, but rather electromagnetic fields propagating through the quantum vacuum at light speed? That the energy powering your computer right now is traveling through the space around the wires, not inside them, and that understanding this distinction reveals secrets about the nature of energy, information, and the electromagnetic force that governs everything from atomic structure to the behavior of stars. This is Stephen Hawking's revelation about electricity, a journey into the heart of electromagnetic theory that reveals how our most familiar technology operates according to principles so counterintuitive that they challenge our basic assumptions about energy, matter, and the nature of physical reality itself. Before we explore Stephen Hawking's analysis of the great misconception about electricity and why understanding the true nature of electromagnetic phenomena reveals some of the deepest secrets about energy, fields, and the quantum nature of reality, hit that subscribe button because we're about to journey into the electromagnetic realm where our everyday experience misleads us about one of the universe's most fundamental forces. Stephen Hawking's approach to understanding the electrical misconception would have begun with his characteristic insistence on distinguishing between useful approximations and fundamental reality. The physicist would have immediately pointed out that while the nut-set-chart-and-flowing electrons model serves as a convenient teaching tool for basic circuits, it fundamentally misrepresents what's actually happening when electrical energy moves through space and matter. The great misconception begins with the idea that electrical current consists of electrons flowing through wires like water flowing through pipes. This hydraulic analogy, while useful for understanding basic circuit behavior, creates a completely false picture of how electrical energy actually propagates. Hawking would have emphasized that this misconception prevents us from understanding the true electromagnetic nature of electrical phenomena. When you flip a light switch, the light turns on almost instantaneously, even if the switch is far from the bulb. If electricity were really electrons flowing through wires, this would be impossible. Electrons move incredibly slowly through conductors, typically at speeds of millimeters per second. The signal that turns on the light travels at nearly the speed of light, which is impossible if we're thinking about particle flow. Think about this like trying to understand a telephone conversation by imagining that the actual air molecules from your mouth travel through the phone lines to reach the other person's ear. Just as sound is really pressure waves moving through air rather than air molecules traveling from place to place, electricity is really electromagnetic waves moving through fields rather than electrons traveling from place to place. The physicist would have been fascinated by how this misconception obscures the true nature of electromagnetic energy propagation. When electrical energy moves from a power plant to your home, most of that energy travels through the electromagnetic fields in the space around the wires, not through the wires themselves. The wires serve as guides for the electromagnetic fields, like the banks of a river guide water flow, but the energy flows through the surrounding space. Recent research in electromagnetic theory has confirmed that electrical energy propagation is fundamentally a field phenomenon rather than a particle phenomenon. The Poynting vector, which describes electromagnetic energy flow, shows that energy moves through the space surrounding conductors, with the conductors themselves serving as boundary conditions that shape the field configuration. Let me ask you something that would have fascinated Hawking. If electrical energy travels through electromagnetic fields in space rather than through moving electrons, what does this tell us about the relationship between matter and energy in electromagnetic phenomena? Share your thoughts in the comments below, because this question reveals fundamental truths about how energy and information propagate through the universe. Hawking would have been particularly intrigued by the quantum mechanical nature of electrical conduction. At the atomic level, electrical current doesn't consist of classical particles flowing through a medium. It involves quantum mechanical wave functions that describe the probability of finding electrons in various states. These wave functions can tunnel through barriers, exist in superposition states, and exhibit interference effects that have no classical analog. The physicist would have been amazed by how quantum mechanics reveals that electrons in conductors don't actually flow in any classical sense. Instead, they exist in delocalized quantum states that extend throughout the conductor. When we apply an electric field, we're not pushing electrons through the material. We're shifting the entire quantum mechanical state of the electron C in response to the electromagnetic field. Recent developments in quantum electronics have revealed phenomena like ballistic conduction, where electrons can travel through certain materials without scattering, and quantum coherence effects that allow electrical current to flow without resistance in superconductors. These phenomena are impossible to understand using the classical flowing electrons Schaaf's model. Think of it like this. Imagine trying to understand a symphony orchestra by focusing only on the individual musicians walking to their seats, while ignoring the music they create together. The classical electron flow model focuses on individual particle motion while missing the collective quantum mechanical phenomena that actually govern electrical behavior. The physicist would have also examined how the electrical misconception obscures our understanding of electromagnetic fields as fundamental entities in their own right. Maxwell's equations reveal that electric and magnetic fields are not just mathematical conveniences. They're physical realities that can exist independently of matter and carry energy, momentum, and information through empty space. Hawking would have been fascinated by how electromagnetic fields represent one of the most fundamental aspects of reality. These fields permeate all of space and time, and matter itself can be understood as excitations or disturbances in these fields. The electrical misconception reverses this relationship, making fields seem like secondary effects of particle motion rather than recognizing particles as manifestations of field dynamics. Recent research in quantum field theory has revealed that even empty space is filled with electromagnetic field fluctuations, virtual photons constantly appearing and disappearing in the quantum vacuum. These vacuum fluctuations contribute to phenomena like the Casimir effect and play crucial roles in atomic physics and quantum electronics. The physicist would have been intrigued by how this field perspective revolutionizes our understanding of electrical phenomena. Instead of electrons flowing through wires, we have electromagnetic fields propagating through space, with matter serving as a medium that shapes and guides field behavior. This perspective opens up entirely new ways of thinking about electrical technology and electromagnetic phenomena. Hawking would have also explored how the electrical misconception prevents us from understanding the true speed of electrical signals. While electrons drift slowly through conductors, electromagnetic signals propagate at speeds approaching the speed of light. This distinction is crucial for understanding everything from computer processors to power transmission systems. The speed of electrical signals depends on the electromagnetic properties of the medium through which the fields propagate. In vacuum, electromagnetic waves travel at exactly the speed of light. In materials, they travel slower due to interactions with atoms and molecules, but still it speeds millions of times faster than electron drift velocities. Recent advances in high-speed electronics have pushed signal propagation speeds to their fundamental limits, revealing the electromagnetic nature of electrical signals. Engineers working on computer processors and communication systems must account for the finite speed of electromagnetic propagation, treating electrical connections as transmission lines that guide electromagnetic waves rather than simple conductors carrying electron flow. Think about this remarkable fact. The electrical signals in your computer's processor travel at significant fractions of the speed of light, yet the electrons themselves barely move. It's like having a message system, where the messengers walk incredibly slowly, but the messages themselves travel at nearly light speed through some other mechanism entirely. The physicist would have been fascinated by how understanding the true nature of electrical signals reveals connections to relativity and the fundamental structure of space-time. The speed limit for electrical signals is ultimately set by the speed of light, connecting electrical engineering to the deepest principles of physics. Hawking would have also examined how the electrical misconception obscures the relationship between electricity and magnetism. The classical picture treats electric and magnetic phenomena as separate effects, but Maxwell's equations reveal that they're different aspects of a single electromagnetic field that exists as a unified entity in four-dimensional spacetime. The physicist would have been amazed by how electromagnetic unification represents one of the greatest triumphs in physics, revealing that electric and magnetic fields are really components of a single electromagnetic field tensor. This unification is impossible to understand using the classical Naughty-Dual flowing electrons Hahn picture, which treats magnetism as a secondary effect of moving charges. Recent research in electromagnetism has revealed even deeper connections between electric and magnetic phenomena. In relativistic contexts, what appears as an electric field to one observer appears as a magnetic field to another observer, moving at high speed. This observer dependence reveals the fundamental unity of electromagnetic phenomena. The physicist would have been intrigued by how this electromagnetic unification connects to the other fundamental forces of nature. The electromagnetic force is one of four fundamental forces, and understanding its true nature is crucial for comprehending how forces work at the deepest level of reality. Hawking would have also explored how the electrical misconception prevents us from understanding superconductivity, one of the most remarkable phenomena in physics. Superconductors can carry electrical current with zero resistance, but this behavior is impossible to understand using the classical electron flow model. Superconductivity involves the formation of Cooper pairs, quantum mechanically bound pairs of electrons that can move through the material without scattering. These pairs exist in a quantum coherent state that extends throughout the entire superconductor, creating a macroscopic quantum phenomenon that has no classical analog. Recent discoveries of high-temperature superconductors and unconventional superconducting mechanisms have revealed even more exotic quantum effects in electrical conduction. These phenomena demonstrate that electrical behavior at the quantum level is far stranger and more wonderful than the classical misconception suggests. Think of superconductivity like a quantum dance, where electrons pair up and move together in perfect synchronization, creating a collective quantum state that can persist indefinitely without energy loss. This quantum choreography is invisible from the classical perspective that focuses only on individual particle motion. The physicist would have been fascinated by how superconductivity reveals the quantum mechanical nature of electrical phenomena and points toward technologies that seem almost magical: levitating trains, lossless power transmission, and quantum computers that operate on principles that transcend classical physics. Hawking would have also considered the cosmological implications of electromagnetic phenomena. Electromagnetic fields play crucial roles in the structure and evolution of the universe, from the behavior of stars and galaxies to the cosmic microwave background radiation that provides evidence for the Big Bang. The physicist would have been intrigued by how electromagnetic fields can exist independently of matter and carry energy across vast distances through empty space. The light from distant stars represents electromagnetic energy that has traveled for millions or billions of years through the vacuum of space, demonstrating the fundamental reality of electromagnetic fields. Recent observations of cosmic magnetic fields and electromagnetic phenomena in extreme astrophysical environments have revealed new aspects of electromagnetic behavior that push the boundaries of our understanding. These observations show that electromagnetic phenomena operate on scales from the quantum to the cosmic. The physicist would have recognized that understanding the true nature of electricity and electromagnetism is crucial for comprehending how the universe works at all scales, from the quantum mechanical behavior of atoms to the large-scale structure of galaxies and the cosmic web. Hawking would have also examined the technological implications of understanding electromagnetic phenomena correctly. Modern electronics, from computer processors to wireless communication systems, depends on precise control of electromagnetic fields and quantum mechanical effects in materials. The development of quantum electronics, spintronics, and other advanced technologies requires understanding electrical phenomena at the quantum level, where the classical misconceptions break down completely. These technologies operate on principles that are invisible from the classical narrow flowing electrons Z perspective. Recent advances in quantum computing and quantum information processing are pushing electrical technology into regimes where quantum mechanical effects dominate completely. These technologies require understanding electrical phenomena as manifestations of quantum field dynamics rather than classical particle motion. The physicist would have been excited by how correct understanding of electromagnetic phenomena opens up possibilities for technologies that seem like magic today. Quantum computers that can solve certain problems exponentially faster than classical computers, quantum communication systems that are fundamentally secure, and electromagnetic metamaterials with properties that don't exist in nature. Hawking would have also considered the educational implications of the electrical misconception. Teaching electricity as free-charged flowing electrons creates conceptual barriers that prevent students from understanding more advanced electromagnetic phenomena and quantum mechanics. The physicist would have advocated for teaching electrical phenomena from the field perspective from the beginning, emphasizing the electromagnetic nature of electrical energy propagation and the quantum mechanical nature of conduction in materials. This approach would better prepare students for understanding advanced physics and modern technology. Recent research in physics education has shown that students who learn the correct electromagnetic picture from the beginning have better conceptual understanding and are better prepared for advanced courses in electromagnetism and quantum mechanics. The physicist's analysis would ultimately reveal that the great misconception about electricity isn't just a harmless oversimplification. It's a fundamental misunderstanding that prevents us from grasping the true nature of one of the universe's most important phenomena. Hawking would have understood that electricity, properly understood, reveals deep truths about the electromagnetic nature of reality, the quantum mechanical behavior of matter, and the field-theoretic structure of the universe. The misconception obscures these profound insights and limits our ability to develop new technologies and understand natural phenomena. Recent developments in electromagnetic theory, quantum electronics, and field theory continue to reveal new aspects of electrical phenomena that are invisible from the classical misconception. Understanding these phenomena correctly is crucial for advancing both fundamental physics and practical technology. The physicist would have seen the electrical misconception as an example of how our everyday experience can mislead us about the fundamental nature of reality. Just as our intuitions about space and time are challenged by relativity, our intuitions about electrical current are challenged by electromagnetic field theory and quantum mechanics. Hawking's investigation would show that electricity isn't electrons flowing through wires. It's electromagnetic fields propagating through space according to the laws of quantum field theory. Understanding this distinction reveals the true nature of one of the universe's most fundamental forces and opens up new possibilities for technology and scientific discovery. The next time you flip a light switch or use an electronic device, remember Stephen Hawking's insight about the great misconceptions surrounding electricity. What you're witnessing isn't particles flowing through wires, but electromagnetic fields propagating through space at nearly light speed, governed by quantum mechanical principles that reveal the deep electromagnetic nature of reality itself. If this exploration of the great misconception about electricity has challenged your understanding of one of the most familiar phenomena in daily life, make sure to smash that like button to support more investigations into the profound truths hidden behind everyday experiences. Subscribe to our channel and hit that notification bell so you never miss our journeys into the misconceptions that prevent us from understanding the true nature of reality. Share this video with anyone who's ever wondered about how electricity really works, because Hawking's analysis reveals that even our most familiar technologies operate according to principles far more profound and beautiful than our everyday experience suggests. And let me know in the comments, what other common misconceptions in physics would you like to see explored? How do you think understanding electromagnetic fields correctly might change how we approach electrical technology? What connections between quantum mechanics and everyday phenomena do you find most surprising? Drop your thoughts below and join our community as we continue to explore the profound truths that lie hidden beneath the surface of familiar experiences, revealing the electromagnetic and quantum mechanical nature of the reality that surrounds us. Phrases de impacto para thumbnail. Is deal 1. Transy electricity isn't flowing electrons imambisiuaux. 2. Nessa nows Hawking's electrical revelation antasacta 3. Mans the great electrical lead in Biscant. Hashtags Stephen Hawking, nerf electricity, electromagnetism, quantum mechanics, physics misconceptions, electromagnetic fields.